All right. Hello, everyone. My name is Alex Ferencich. I am a postdoctoral researcher at UC San Diego, and my research is primarily in data center networking and optical switching, things like that. I'm the maintainer of the Corundum high-performance open-source FPGA-based NIC, and today I'm going to be talking a little bit about cocotb. So cocotb is a Python package that allows you to connect basically a test bench in Python to a HDL simulator. So it says it here specifically for writing VHDL and Verilog test benches in Python, but it's really just a technique for connecting to an HDL simulator. So cocotb provides a couple of different features. The most important one is it connects to the simulator API. So in Verilog simulators, you have something called VPI. In VHDL simulators, you have something called VHPI. Now, I'm not actually sure what happens if you have a mixed language design. Do you use both, or do you just pick one? Not sure about that. Anyway, what cocotb does is it provides a high-level Python abstraction, an object-oriented abstraction. So when your test bench starts up inside the simulator, you have a device under test reference that points to basically the top level module in the design. And then you can go traverse down into the hierarchy, and you can read and write signals inside the design. So using this, you can write code in Python that can exercise a test bench, or that can exercise a design in Verilog or VHDL that's running inside the simulator. So why would you want to do something like that? I mean, it is possible to write test benches in Verilog or VHDL, but here's the thing. Have you ever actually tried to write a non-trivial test bench in Verilog or in VHDL? It sucks. It's the languages are, I mean, if you're talking about writing a design that's going to be loaded on an FPGA, so it has to be synthesizable, Verilog and VHDL, they work fine. But if you're talking about setting up queues and performing, various computations in the test bench, it doesn't need to be synthesizable. There's all sorts of limitations that VHDL and Verilog have that you're probably going to run into. And working around those can involve writing a whole lot of additional code. It can be kind of problematic. However, if you can work in a language like Python, then you can pull in standard libraries and use all sorts of language features that make it much easier to write, your basic test cases. For example, if you're working with DSP components and you want to build a filter or do an FFT, well, that's just a couple of lines using NumPy. But if you wanted to write that in Verilog or VHDL, that's going to be a much more complicated and non-trivial piece of code. And you'd have to do some tests to make sure that your test bench is working correctly, and it's just a pain. So with cocotb, what you can do is create your test bench in Python, and I just have the cocotb GitHub page up here, so you can have a very simple Verilog design, and then you can write Python, which in this case it's doing basically the same thing that you would do in a standard HDL test bench, where you can create a clock, and then you can drive some values into the design and check to make sure that you got the expected values back out. So this one is a very simple example, but what I'm going to do today is build some more complex test benches, hopefully. Let's see. So the other thing that you need to do when you're making a test bench is not only have access to the signals inside the design. So in this case, we can access both the D port and the Q port, right? There's Q, there's D, and they can be accessed just directly through the dot object. But you also need to be able to interact with the simulator in terms of timing. So in cocotb, they use the async and await syntax. So the functions are defined as async, and then you can await different events. So in this case, you can await for the falling edge of the clock. And then you can also start up what are called coroutines which basically run in parallel. Not exactly. At any given point in time, only one piece of code is going to be running, but all the other ones are going to be basically awaiting an event. So in this case, this will start up a coroutine that drives the clock. So every 10 microseconds will generate a clock edge. Well, let's see. So yeah, so it generates a clock with a period of 10 microseconds. So it'll generate a rising edge, and then 5 microseconds later, a falling edge, 5 microseconds later, rising edge, so on and so forth. Okay. The other thing that cocotb has is a build system. So the thing with VPI and VHPI is the way you use them is you build basically a shared object file that gets loaded into the simulator. Once it runs inside of the same process, then it has access to all of the simulator APIs. So setting all this up requires actually building the shared object and setting up the simulator correctly and pointing everything at the right place. So cocotb also has a makefile infrastructure that automates starting up the simulator. So this one points at the let's see, it points at the Verilog or VHDL sources, and then it also points at the testbench module. So test dff.py points at that, and then you include the cocotb makefiles, which actually do the rest of the work and set everything up. And then you can run it, and there's this, and then it will start up the simulator and run the design. Now, actually, one thing I should mention about cocotb is that it supports a very wide variety of simulators. So previously, I was doing something very similar, writing test benches in Python for HDL designs running in other simulators, or running in an HDL simulator using a framework called myHDL. But myHDL is designed primarily for generating Verilog and VHDL, and their co-simulation thing is a little bit of an afterthought. So it has some disadvantages. And one of the big ones is that it only supports a very limited number of simulators. So I think last time I checked anyway, you could co-simulate myHDL Python with like Icarus Verilog and GHDL, and that's about it. But cocotb supports, if they have a list here, I have a list somewhere, maybe they have a list here. Well, they have a list somewhere of all of the simulators that are supported. So they support not just Icarus Verilog and GHDL and Verilator, but they also support a bunch of commercial simulators. So Model Sim, Quest Sim, and a few others are also supported by cocotb. So that means that if you build a test bench in cocotb, you can run it against all of these different simulators. Now, for all of you open source aficionados, you might be wondering, why do I care about using commercial simulators? Well, occasionally you might need to use closed source or vendor IP for various reasons. For example, if you want a high performance PCI Express interface, well, then you might need to use the vendor provided PCI Express IP. And you can't simulate that in any of the open source simulators. You have to simulate that in one of the commercial simulators. So if you actually want to simulate that as part of your design, even if everything else is open source, you have to use a commercial simulator. So for all of my designs so far, I usually separate things out. So I have some top level code in FPGA.v. And then inside of that, I have a module called FPGA Core. So FPGA Core is 100% Verilog, and you can run that on anything. It works just fine in Icarus Verilog, and it would probably work just fine in Verilator. Versus FPGA Core actually pulls in all of the vendor IP. And I basically only test in simulation FPGA Core, and then I test FPGA.v on the actual hardware and basically hope that it works. So with cocotb, this actually opens up the possibility for doing a simulation of the complete system that includes all of the vendor supplied IP. And that can be useful for working out issues and interfacing and things like that, as otherwise you're basically limited to either just guessing or using the ILA. And actually, usually a combination of the two because ILAs are kind of limited. All right, so now that I've presented a little bit of background on cocotb, what I want to do is put together a test bench that uses cocotb. So we have an example for how to do some more complicated stuff in cocotb. So I will say that I'm a relatively new user to cocotb. I've only been using it for the past couple months, although considering the current situation, it doesn't really feel like just a couple of months. Anyway, so what I've been doing is slowly converting all of my test infrastructure over to cocotb. So as part of that, I've actually created several different cocotb extension modules. I have cocotbx AXI. This one supports AXI, AXI Lite, and AXI Stream. So if you're using one of those interfaces inside of your HDL, then you can connect to that with cocotb using this. There's also cocotbx Ethernet. This one supports all of the kind of standard PHY interfaces. So MII, GMII, RGMII, and XGMII. Eventually, I'm going to add support for serializer-based stuff. So primarily 10G, 25G Ethernet, but we'll see. Possibly some other stuff as well. And then the big one is cocotbx PCIe, and this is one that this one basically has its own kind of simulation framework inside of it that simulates a PCI Express subsystem where you have a bunch of different components talking to each other. You have the root complex, might have the drivers, and then you can have PCI Express devices, and they can communicate. You can do MMIO, peer-to-peer DMA, or whatever. And getting this to work in my HDL originally was a bit hackish because it's missing a few nice features that you have in cocotb, like cocotb.fork. So some things were a little bit annoying to do here. So I was like, yeah, it's a bit of a hack to make it work in my HDL. I don't know if it's going to work very well in cocotb. Actually works a lot better in cocotb. So I have it all nicely formatted and organized up here. So now that I've moved over to this, and actually I will say this was kind of the motivation for moving over to cocotb because we need to, as part of the research, run some code on Stratix 10 DX devices. So in order to do that, we need to make some new simulation models. And I figured, all right, maybe it's time to look at moving over to cocotb now so we don't move later and then have to port all of these new modules as well. We can just move everything over to cocotb and then write the new stuff under cocotb. And I think that's been a pretty good decision. Let's see. So these are the three main modules that I put together for cocotb, and then I've been slowly porting over the test benches for all of my Verilog code. So this one I'm in the process of porting. The AXI stuff has been ported, PCIe stuff. I have all the cocotb test benches up there now, and then Corundum has also been ported to using that. And the other nice thing about using cocotb is it's relatively easy to connect to GitHub Actions. So with this, we can run all of the integration tests automatically. So every time you push some code up to GitHub, it will run all the tests and confirm that yes, we didn't add any new bugs. So that's pretty useful. I've been working with some of the cocotb maintainers to try and streamline this process a little bit. And there's a very useful plugin called cocotb test. And this one, it basically replaces the makefile interface for cocotb and moves it into Python. Probably thinking, why the heck would you want to do that? Well, the main advantage is because this allows cocotb to be used with pytest. It basically means you can run the simulator from Python, which means you can do a bunch of pre-processing before you actually hand it off to the test bench and to the simulator. And one of the things you can do with that is you can expose the test benches to pytest. And one of the things you can do there is you can parameterize module parameters and things like that. So instead of running your test bench once, you can actually have it set up to run the test bench 10 times with different sets of parameters. And that is an incredibly powerful capability. And we take advantage of that here. The other thing is that you can use a trick another package called pytest split that allows you to basically split up the tests into a bunch of groups. So in this case, I actually have 10 groups run on 10 different instances on the GitHub system, and that basically allows the test to run 10 times faster. So we've done a bunch of work there to try and make this a little bit more reasonable to run some of these non-trivial tests. But yeah, everything's coming together nicely. It's not quite finalized. There's still a few odds and ends that I'm still working out. In fact, I'll talk about that in a little bit. But for now, let's take a look at a current cocotb test bench and then write a new one. So this is the Verilog Ethernet repository that I have here, and I've been slowly converting all of the test benches. Here, this is all of the test benches here, and actually I can shrink this list a little bit. Let me get rid of some of the output files. Okay, so these are all of the old MyHDL test benches for all of the modules in Verilog Ethernet. And as you can see, I've got basically two versions of a lot of these, right? I have a normal one and then a 64-bit one. Now previously I actually had two different versions of the modules. I had a normal one, an 8-bit one, and a 64-bit one. But I'm slowly going through and converting all of the modules to parameterized modules. And when you do that, then the only thing you need to do is change the module parameter, and everything else is exactly the same. So if I compare, these two Python files, the 8-bit one and the 64-bit one, compare with active tab, you can see that there's exactly two lines that are different between the two, right? They are exactly the same except for the name of the test bench and the parameter. That's it. Everything else is exactly the same. So in this case, we can get a huge benefit from cocotb because you only need one test bench here. I don't need two. And I can use cocotb test to run both of these parameters. I can run the test with both values of data width. And actually, it becomes trivial to run it for like 10 values of data width if you want. So let me show you a cocotb test. This is for the this is for handling Ethernet frames. So let me pull up the Verilog file first. Okay, so this is the Ethernet frame receive module. So this brings in an AXI stream interface that contains the Ethernet frame, and it extracts the header and the payload, and those come out separate interfaces. Relatively simple. But this one has a parameterizable data width. So this same code can be used for 8 bits or 64 bits or 512 bits or whatever. Test bench for this, you can see down on the bottom, this is how you connect it to cocotb test. So this is how you call the simulator. And right here we can add pytest.mark.parameterize. And I can put in 1, 2, 3, 4, 5, 6, 7 different values of the data width. And this will run a test with all of those. Which is very useful. So let me just run that real quick so you can see what that looks like. This terminal here, I have watching what processes get started up, so we can see everything starting and running. Okay, so I'm going to do, I don't want to do make. I can do pytest. I'll run that like that, and it will run all the tests in parallel on different CPU cores. So there we go. All 7 tests started. Now they will terminate one at a time as they complete. So there you go. So we have one test bench here that we can run trivially with a bunch of different parameters. So yeah, this is a hugely powerful capability. Now, if you're debugging, you might want to run just one test case and look at it more in detail. So this is why I kept the makefile infrastructure. So I can run make, right? And this will go ahead and start the simulator. And now you can actually look at the debug output while it's running. I'm going to stop this, and you can also set this up to generate waves. Let's see. Gotta make it clean first. All right. Make. So if you add waves equals 1, now it runs with the waveform dumping enabled. So I'm not going to let this run to completion because this takes a while. But this dumps out this FST file, which contains the waveforms. So I can now open that up in GTK Wave and the second go, and we can see all of the waveforms that are generated as the test is running. So yeah, this is pretty useful. All right, so what I'm going to do here is I'm going to create a oh, that failed because I didn't make clean. All right. Okay, so what I'm going to do here is make a test bench for some of the code that doesn't have test benches yet. Well, it has test benches, it just has myHDL test benches, so I want to make new ones for cocotb. So similar to this this Ethernet code, I have some ARP layer code. So I have ARP ETH RX and ARP ETH TX. So in this case, for the RX code, you have an Ethernet frame, and then at the output you get all of the fields pulled apart. So this is a prime candidate for a very similar test bench. Then I also have a high-level test bench here, ARP, and this integrates both the RX and the TX and the ARP cache. And this one, this needs to do a couple different things. It needs to respond to ARP requests coming in from the network and send their corresponding response packet back. And then it also needs to perform lookups. So other pieces of the code might need to look up the MAC address for something, for a particular IP. So it'll provide the IP here, and then the ARP code either needs to return the response out of its cache or perform the ARP request lookup. So all this needs to be tested to make sure it's all working properly. And again, this one has a parameterized data width, so we want to run against a bunch of different widths to make sure that everything works. And we don't have any bugs that are specific to a particular configuration. All right, so what I'm going to do is make a copy of one of these existing test benches, and we'll go from there. All right, so do cp eth access tx to arp eth rx. All right. Oops. I need to copying a directory here. All right. So this is the arp eth rx module.v. So I'm going to go down here and pull up arp rx here. Okay, so I got both the makefile and Python file. I'm going to rename this. Okay. All right. Let's see. All right, so here's a Verilog file. This one's called arp-eth-rx, and it's got 3 different parameters. And I think those parameters are the same. So the parameters are here. We got data width, keep enable, and keep width. I need to change this to match. And it doesn't pull in any additional Verilog modules. So one thing I will mention is that I'm considering getting rid of these make files and then only using cocotb test, although I haven't done that quite yet. So it's on the to-do list. Okay, so here is, why is it saying that's in a different directory? All right, so, because I have the myHDL test open. I see, okay, that's fine. All right, so down here, I need to do the same thing. This needs to be converted to arp-eth-rx. There we go. All right, so run this against all of the various widths, and I think that'll work. Okay, so let's just go over everything that we have in here. So the imports, we're importing a few things. Some of these are used just inside the test bench. For all of the packet processing stuff, we're using Scapy. So previously, for the myHDL stuff, I actually kind of wrote my own packet handling code in Python. That was kind of a pain because, if you're testing both the test bench code and the Verilog code, if they match, that doesn't necessarily mean that that what you have is going to work if the Python code that you have as a reference is wrong. So By using scapy, I can be reasonably certain that that this is actually a good reference. Let's see, and then we have pytest and cocotb test.simulator. These are used down here. Pytest just for the parameterization, and then cocotb test.simulator to fire up the test via pytest there. And then this is the stuff used from cocotb. So we've got the clock object, we got rising edge, and we got test factory. So let's see, test factory. All right, so clock, this is used to generate the clock. Rising edge is what you use to wait for a signal to change. So basically the only way I use that is to wait for, rising edges on the clock. So you might use that in, in a Verilog test bench as well. You can just wait for, a rising or falling edge. Let's see. And then what else did I have up here? Right, and then test factory. So cocotb has some test management stuff built into it, and that's important because this has to run inside of the simulator. So you're kind of using, when you use cocotb and you're using cocotb test running under pytest, you're basically using two different testing frameworks at the same time. So pytest is used to manage which simulator runs you're doing, but then inside of each simulator run you have cocotb and its internal regression management system that's responsible for running all of the test cases within the simulator. I'm not sure if it's even possible to have, pytest drill down into the simulator and manage that as well. I don't think there's really a nice way of doing that. So kind of a little bit of a necessary evil. So there's a little bit of a replication here. So some of the stuff, so this is basically doing the same kind of thing as pytest.mark.parameterize, except this is over separate runs, and this is within each run. So in this case, we have a set of payload lengths that we're going to run. This is size list, so you can pick some useful sizes to test. Payload data. This is the the data that we're going to be generating. Idle inserter and back pressure inserter. These are then used to generate some back pressure to check to make sure you don't have any issues with how the back pressure is being handled. So with this setup, this will actually generate 4 different tests because these only have one value, but these have 2 different values. All right. And then this runs the actual, so let's see. And there's 2 other pieces here. This one is kind of a little test bench helper object. You don't need to create one of these, but it makes things a little bit simpler because you can set this one up to point at the, you can create a new one of these based on the .dot object, and then this one kind of has all of the standard code that that you want to run. So in this case, this will set up logging, it'll start the clock, and it'll create a lot of the simulation models that you need. If you want to have multiple test cases, then this is where the power of this object comes in, because you can pull this code into every single one of your test cases and reduce the amount of duplication that you might have otherwise. And then this also has some, this also has the idle generator and back pressure generator stuff that passes these inputs through to modules. So in this case, I don't need to go through and set both of these sources and sinks inside of each of the tests. That's all just centralized here. And then also the reset handling. So this makes things a little bit simpler. You can create the .dot object, you can wait for the reset routine to run, and then you can actually run the test. So name of the game, at least for me, when making test benches like this in Python, is to make them as short as possible, right? The less code you have here, the less duplication you have across all the test benches, the easier it is to manage. All right. Oh, I see Thomas from one of the cocotb maintainers is saying that there are some ideas to use pytest as a regression manager inside cocotb. That could be useful. I guess we'll see how that works going forward. Yeah, especially for using pytest and cocotb test outside to be able to use cocotb test inside. That could make things simpler. Although there is one kind of nice feature about the way things are currently set up, is that I have one Python file here that's basically serving 2 purposes. You can kind of think of this as 2 Python scripts in one. There's this one here, which is cocotb test. And then everything up here is the actual test bench. So if you were to use pytest for both of these, you might run into pytest detection issues, right? Because you don't want pytest detecting this test case. You only want pytest detecting this one, because this one here has to run inside of the simulator. So there's definitely a few issues that need to be thought of. I guess we'll see what that looks like. Okay, so what about the actual test case? In this case, what we're going to do is generate a bunch of Ethernet frames that contain ARP payloads, and then we're going to pass that through the ARP ETH-RX module, which should peel off all of the ARP header fields. Okay, so let's see. Right now, we're creating just a raw Ethernet frame, and this is using scapy. So if we go up here, this is using ether from scapy.layers.l2. So let me go pull up a test bench that has some ARP code in it that we can copy from. Let's see. Pull from this one. Okay. So, all right. So ARP is also in L2. Okay. And let's see. So this is one of the test benches for one of the example designs. So I can actually run this just so you can see what it looks like. Do anything particularly complicated. It just resets everything, and then it sends a UDP packet into the test bench, and it gets an ARP request, right? So this is ARP request here. So you see RX frame and RX packet. RX frame comes from the XGMII sync module. So Verilog design drives the frame out via XGMII. This receives it and stuffs it in a FIFO. And then the test bench takes over and it stuffs it through scapy, which produces a packet object. So you get two outputs here. This one is the raw bytes, and this is the parsed packet. So this one, as you can see, contains an ARP payload, and then it generates an ARP response. It sends it back. There's the raw bytes that get sent back, and then the actual packet comes out, which is a UDP packet with a raw data payload. Right. So what I need to do now is generate a ARP request. No. Well, I just need to generate ARP something. Doesn't matter if it's a request or a response. So I need to do something like this. Okay. Push the button I didn't want to push. Okay. So let's see. Here is the Ethernet code here. Let's see. So I'm going to go ahead. I have the Ethernet header. Keep that the same. Actually, so I'm going to remove the type field, and I'm going to let scapy figure that out. And then I need to put in some stuff here. So hardware source. So this is the source MAC address, and then the source IP address, and then again the destination MAC and IP addresses. So I guess what I should do is take a look at what the Python, the original test bench looked like in MyHDL. I think that's right. Yeah. Okay. Okay. Well, I guess if we're doing, all right, hang on a second. Let me pull up the original test bench in MyHDL. Okay. And we can just do the same thing that this is doing. All right. So this, let's see. This is going to send an ARP frame operation of 1. Got 64, 165 for IP addresses. Okay. Not too bad. All right, test packet, this, oh, instead of payload, I'm going to put ARP here. All right, so that creates a test packet. All right, so we create the Ethernet header, we create the ARP header, concatenate them together, and scapy has this kind of weird syntax for concatenating headers together. I don't know why they had to go recycle the division operator, but that's what they did. So there's probably other ways of doing that, but this is like their shorthand. Create the test packet, and then if you call build, it gives you just raw bytes. Okay, and then we are going to generate the Ethernet header, right? So ETH header transaction, we take the header, and then we send that through the header source and the payload source. So the header source, this is something that I'm probably going to peel off into a separate repo at some point. This right now is inside of the AXI repository, or the AXI plugin, because this was basically developed to support all of the streaming channels that are used for AXI. So AXI you can think of as it's basically 5 streaming channels running in parallel, and they're all exactly the same. They all use the exact same, AXI stream style handshaking. So instead of duplicating all this code, I figure I'm just going to make a very clean way of generating this. Actually, I can show you what that looks like in cocotb AXI. See, I go look at this here under AXI. Oops, why did that open up a new window? Anyway, so there's AXI channels is what I wanted to click on. So this is how you define AXI. Look at this. This is what, 30 lines of Python code that generates the sources and sinks for all 5 of these channels, and then you can use those very easily inside of the actual models. So I have AXI master and an AXI RAM that both need to use all these channels. So in this case, it just takes, hey, you just define the interfaces here, and then you can very easily send and receive. Let's see here. This is process write. One will be calling, AW channel dot. Well, in this case, I called .drive. That's going to be going away at some point. That'll be .send. But yeah, it makes things much more efficient in terms of code reuse. So we can use this to set up, let's see, the Ethernet header, and then, I guess I need to create one of these for the ARP packet as well. Let me see. So this is going to be the ARP frame fields here. Okay. And I may need to go through and rename some of these a little bit. We'll see. Okay, those are all of the fields here. This is going to be now, I'll just call it ARP header. Okay, cool. So, I need to get rid of all the M's. Okay, excellent. So I can take all that and put that in here. Let's see, so that's all of the Ethernet stuff, and then all the ARP stuff is here. There we go. That looks good. So now we can do the same thing on the ARP side. So I'll call this now sync. It's going to be ARP header sync. I think this one is just going to be M here. So one cool thing about cocotb is they've got a bunch of helper modules and helper functions, and one of them is something called bus that can go through and basically match signals based on a prefix. So this is what I use for all this stuff here. For this one, it will look for SETH, and anything that ends in that. Well, okay, so in this case, the ETH header source has this list of all of the signals that it's looking for. So you give it a prefix, SETH, and then it goes ahead and it prepends that to all of these. So it'll do SETH header valid, SETH header ready, so on and so forth, and it will check to see in the Verilog file, well, I guess not for the Verilog file, but in the simulation model, or in the simulator state, it will look for signals with those names and package them up into an object. So it's very easy to use. So yeah, it'll go in and it will try to match, these signals. But yeah, I didn't name these particularly well. Maybe I'll go in and change that at some point. But yeah, so this one, it does the same thing. In this case, the only common prefix is M. So maybe I'll have to go tweak that later. Okay. So I think this will work. I guess I don't need that. Like 8 is complaining about stuff as usual. Okay. So I'm going to go ahead actually and comment this stuff out. Add a print here for RX frame. And well, let's see if it runs. I don't need that. Probably going to blow up my face. Oh, this is actually doing something. Okay. Wait. That did not look like it did the right thing. Well, I guess one thing to... Oh. Okay. I see. Alright, so I need to change this to actually send the payload of the Ethernet frame. Let's see. What would you do for that? I think that's going to be probably test packet payload build. I think that's what you want to do. Yeah, okay, there we go. That's more like it. Okay, so this is all sending packets of the same size now because, all right, so in this case, I might need to add some more test cases to test with, you know, truncated ARP packets and things like that. So right now I'm actually going to simplify this here. I'm not using that anywhere. So, all right, so there we go. There is a transmitted frame. And then what I'm going to do is now I need to check to make sure I got what I was expecting. So what is this going to do? This is going to give me all of the individual fields. Now I need to check to make sure those individual fields match. Okay, so first thing I'm going to do is I'm going to replace this print. Did I? Okay, so you can actually see it did come out here. It was captured by the sync. These are all of the field values. So that's some progress. All right. Go ahead and I'm going to put RX frame here. Okay, now I need to add a bunch of asserts. So here's test FPGA core, and this is just doing stuff based off of ARP frame. All right, how did I check that? EX or what do I want here? The RX module, I think, right? Yeah, okay. So this one, I need to do something similar. How did I do this? I plugged in. Okay, so I generated another packet and then I checked to make sure that the packets were the same. Okay, fair enough. And then this one came out of all of the frame stuff here. Okay. All right, so I'm going to go ahead and try that. So this is where you got to be a little bit creative, is to figure out how you're going to check to make sure everything worked as expected. So this is going to be frame. Okay. Then I also need to do ARP frame now. ARP. Okay. Set all the fields here. RX packet is the ARP would be, oh no, sorry, that's also ETH. This will be ARP. Okay. So we've got a bunch of different fields here. We got HW type. Gave HW type, is that in here? Oh, I guess ARP H type. And the field names are a little different. Go figure. Go ahead and extract all of these. All right. These are going to be all coming from RX frame. Okay, and then all of these are going to be, need to convert all these to, okay. Okay, and these are going to be arp.something. So H type is HW type. and p-type, that's p-type, and hlen is hwlen, plen is plen, operation up. Then we got hardware source, hardware dest, and protocol source, protocol dest here. Oh no, never mind. That's sorry, source, hardware. All right, that should be PSRC, and this one is HW dest. Okay. All right. So now I'm gonna check to see if this matches here. Okay. Again. Oops. What did I screw up? Oh. Rid of that line. All right, let's run this again. Didn't like something. Oh, because these should be I fix these with ETH. Dest Mac tape. All right, and then I think I need plug in a couple of these as well. So the hardware addresses are going to be like that, and the protocol addresses are going to be like that. Is there anything else I need to do? Operation, ELEN, WLEN. I think all of these are just 1 byte. Maybe not. We'll see. Oh boy. Something was not happy about that. Unless maybe... Alright, how did I do that in the other test bench? At the... in there somehow. Oh, I want this test bench, yes. Oh, it's smart enough apparently to just pull out an integer for that. Alright, never mind. Try that. Yeah, okay, there we go. So we now have a packet. I think that's right. Let's now see if it matches. And there we go. So it worked. The assert didn't fail. So there you go. And now what I can do is go through and add some additional test cases that add padding bytes at the end of the frame to make sure that doesn't screw anything up, and shorten it to make sure that gets caught correctly. So you can go add a lot of additional test cases. So let me see what happens if I run this under pytest. This should go through and run all of the different data widths. So yeah, there we go. So this one just runs them one at a time, but it's just doing 1 test case. So there you go. So this module works with all of those different data widths. So there you go. That's pretty straightforward. Let's see here. That as well. Go. All right. So I got to do a little bit of cleanup work on this, but this is basically the complete test bench for this module. You know, all the basic stuff works. We've got the sources and the sinks for the interfaces that the module provides, and then we also have all of the the basic test cases to test that. Next step is to test the corner cases, but all right, so let's see. I've also got the ART module that I could do, and I've got one thing that I would like to do at some point, and I guess I could do that on the stream if people are interested, is to make a UART extension for cocotb and basically go through the whole process. That'd probably be more interesting than just going through and writing up another module. All right. So if you do want to make a module for cocotb, right? In this case, we're talking about something that's similar to the AXI stream source that you can import and then use. I'll just go over how to do that by making a module on the stream here. Okay, so make a cocotb extension. This is cocotb ext is what's called a meta package. So Nice thing about that is you can actually have multiple Python packages that all get imported through the same kind of top level. Was it meta package? No, it's a namespace package. That's right. Yeah. So you can have multiple packages that all get imported through the same kind of common prefix. So the way you do that is it's just a directory in the Python package. We'll create a cocotbx directory, and inside of that, make a UART directory. Okay. And then inside of that, I can create the actual code. So I'm going to create two files. Init.py file for the actual package. I'm going to create a UART.py file for the actual model. And then I'm also going to create a very important tests directory so we can actually test it. Okay, and I have a folder in there as well. All right, so let's see. In the init.py file, well, right now I'm going to leave this blank. Then the UART file, what we need to do is create an object for each one of the simulation models that we want. All right, so in this case, I'm going to create class UART source. Anything else there? Okay. Okay. So this is going to accept basically one data connection, right? Because for UART, you either have a TX pin or RX pin, and that's it. Oh, Tomas wants to see the waveform view. All right, that's a good idea. Let's go do that real quick, and I'll come back to this. All right, so let's pull up the waveform view of this. I gotta run the test again. Make sim waves equals 1. All right, that runs, and I do GTK wave arp eth rx. All right. Okay. So this is what it looks like. Actually, the nice thing with this test is that I'm only doing one test case per run, so we can actually see everything that's going on. So like I said, this generates 4 test cases, right? Because we have 4 different combinations of the idle and the back pressure. And we can see 1, 2, 3, 4 transfers taking place here, just looking at the activity. What's the best thing to look at here? Like the S ETH payload access T ready and T valid. Here's T valid. Yep. So there we go. Those are the payloads being transferred. So we've got 2 being transferred. And this one, let's see. So we've got idle, and we got an idle inserter, and we get a back pressure inserter. So the idle inserter, this will stall whatever the input is. Back pressure inserter will stall whatever the output is. So in this case, the input is let's see, both the header and the payload on the Ethernet side. So in this case here, we can see that the ETH access payload valid, this is cycling. So this is the idle inserter doing its job. Then on the other side, we can see M frame ready cycling. So this is the back pressure inserter doing its job. Okay, that's pretty straightforward. And then we can go through and look at one of these test cases and just see what's going on. So in this case, what we do is we provide the input MAC address here. Let's see. So we've got you get the source and destination MAC addresses here that get transferred in, and we also have the Ethernet type, right? So the MAC address is an Ethernet type that get transferred in, and then we also have the payload data that gets transferred in, and then the module is basically just storing them by piece inside of all of the internal signals. So as the frame comes in, it will store the source and destination addresses, and then it will store the hardware type, or the hardware address type, the plen, p-type, hlen, plen, all these fields, and then it'll build up the MAC addresses, right? So it's this one, right? As I go 1 byte at a time, it fills up, and then the next one, or I guess this is a IP address, that one will fill up, and then the next MAC address, that'll fill up, right? And then at the end, it has everything, and it can mark the output frame as valid. Here's M frame valid. That's high, indicating that frame is valid and can be checked by the test bench or by the next component in the chain. So that's how that works. And okay, I guess one thing I can show you about how the makefile works is we can override the parameters. So watch this. I can make clean, and I can run it again, but I can do param data width equals, say, 32. Let that run. I go ahead and open it up. And actually, I guess one other thing I can show real quick is that source and sync modules, or at least a lot of the modules that I have, they print out a little bit of identifying information when they start up. And this includes data width. So we can see that, oh yes, it did actually change the data width. If we go up to the last time I ran this, we can see that, here we go, data width 8 bits. In this case, we got data width of 32 bits. Okay, so if I go ahead and pull this, we go ahead and pull up the signals again, we can see that here's the data width is now 32 bits. Now if I open this up, there we go. We got fewer cycles now because it doesn't take as long to transfer the data, because we're transferring it 4 bytes at a time. And you can also see that these fields are built up, 4 bytes at a time instead of 1 byte at a time. So yeah, that's how it works. You can very easily run this with different combinations of parameters. So what I was mentioning before is that I want to get rid of these makefiles, because with the makefiles we have a lot of duplication here, right? Specifically, all the parameters need to be specified here, and all the files need to be specified here, and then they also need to be specified in the makefile, right? We have the parameters multiple times, and the source is here. So cocotb test actually supports doing this stuff automatically. You just give it a this is generating the actual arguments that are sent to the simulator. So in this case, you build up this parameters list or dict, and then you hand that directly to cocotb test.simulator.run, and it will do this stuff automatically. So if I can get rid of the makefiles, that means less code per test bench. It makes things simpler and easier to maintain, and yada yada yada. So what I want to do at some point is to add basically a command line interface to the Python script directly. So instead of running make and make clean, you can just run this script directly with whatever parameters you want to use, and it'll run that. And unfortunately, it's a little bit complicated to do that because, well, for a couple of reasons. One of them is that you basically need to have 2 entry points. One of them for pytest, because pytest sticks a decorator on here, which means you can't really use it for anything else. So we'll have one entry point just for pytest, then we'll have a different one for basically a main method that can handle the command line parameters. And then the other issue is that what we want to be able to do is override parameters. And for the parameters that we don't override, we want to be able to basically kind of do a default value computation based on the other parameters. But if you override it, we don't want to do that. So we need to find a kind of clever way of doing that that doesn't involve a whole bunch of duplicated code in every single test bench. So playing around with some ideas with that, but once that comes together, then I'm hoping to get rid of all these makefiles, so we can just use cocotb test for everything. And then I will say in this case, it's I have one Verilog file, I have a couple of parameters, not really a big deal. But if I go, say, I have one of these, well, I guess I can pull it up over here. If I say go in here, well, where's a good one? Well, so I've got some modules with lots of files. So this one has a whole bunch of files. It's at the bottom. Yeah. Okay. So that's a pretty long list of files. That also has to be duplicated makefile, and keeping those the same is kind of annoying. It's be nice just to have one list of files. In this case, there's no parameters, but for other modules, there are a whole bunch of parameters. So if I go, say, to here, B, and if I go to PMA interface module, for example, this one has a huge list of parameters, right? That's a huge list of parameters, and some of these have pretty non-trivial default computations. Dealing with that is kind of a pain. And in the make file, some of these actually I need to call into Python to compute these values. So if we can just roll all this into Python, it makes it a lot easier to work with. I can say, yeah, I just want to run this with a different data width, or I want to disable the sequence number and make sure it still works, or change the one of these address widths or whatever. So with the make file, I can override any of these and it works. But we'd like to do the same thing in Python because it would make it more maintainable. So that's kind of a long-term thing that would be fun to do at some point. Hopefully we'll have that working soon. All right. Anyway, back to working on the UART module. If anybody has any questions about anything, just stick it in the chat and I'll get back to you, as soon as possible. Okay, so let's see the UART source. The idea here is that this is just a standard Python object. So when you create it, you'll specify the data signal that you want to connect to in the design, and then we'll also specify, say, the width, or sorry, the speed. So 9600 BPS or whatever. Okay, so we'll start with that, and then what we'll do is create a logger. Let's see. Import this as well. Okay, so go ahead and add that import there. Import logging. There we go. Okay. So cocotb just uses standard Python loggers, which is kind of nice. Okay, so we're going to take the data. We're going to add path. So that gives you a nice nice prefix for everything. So say if you have multiple instances, you can tell exactly what signals they're connected to. Okay, and I'm also going to save self.data, and self.baud. Okay, there we go. All right. Now, for the UART, we're going to have to store some of the incoming and outgoing data somewhere. So one way to do that, or the highest performance way to do that, is to use a queue. Oops. All right, so this is from collections. I can type. Okay, there we go. All right, and we also need some stuff from cocotb, so I'm going to go ahead and import this here. Import cocotb. And then we're going to need a bunch of triggers. So from cocotb.triggers, import. I think rising edge will need event, probably, maybe some other stuff. Yeah, timer, definitely. Okay. All right, so create this guy. And then the other thing we need is some synchronization components. So when you're going to, well, we'll come back to that in a minute. Okay, so when you want to send something, we'll use write. And then we're going to take that data and we're going to put it inside of the queue. Well, actually, I'm going to create two functions here. Okay, that one's going to be the actual implementation. So this is something that I'm just trying to be consistent across all the modules that I make, and by providing both a blocking and a non-blocking version. And the blocking versions don't necessarily block, but they are async. So if we make them blocking at some point, it'll actually work. So the idea with this is that you'll be able to specify, say, a maximum queue size, and then it'll block if that's exceeded. Okay, so write no wait, and in this case, what we're going to do is self.queue.end. So we're going to take all the data bytes and stick them in the queue. Okay, and now we need to tell the module that there's actually something in the queue. So I need to create a event. Okay. So far, what we've defined here is basically the interface to the test bench. And there's some other kind of helper methods I can add here, which I won't bother with for the time being. I'm just kind of doing the minimum that's necessary to make this work. Okay, so that's what I have so far for the source. I'm going to go ahead and put the same kind of stuff in the sink, and then go from there. All right, so UART sync. The same thing. We got everything the same, except instead of write and write no wait, we're going to have read. Okay, so async def read self count will be -1 by default. Okay, and then I need also async def read. Oops, not async. Wait. Okay. All right. So the idea here is you can attempt to read a certain number of bytes out of the internal queue. All right, so read, we can't simply call read no wait in this case. Eventually, we will do that. We will return self.readNoWait with the same count parameter. But before that, we need to make sure that the queue is not empty. So what we can do is while the length of the queue is 0, we await the synchronization signal. So I can do self.sync.clear and then await self.sync.wait. Okay. And then read no wait, what we're going to do is pull stuff out of the queue. So let's see here. If count, first thing we need to do is make sure that we're not going to try and read more than the size of the queue. So self.queue. All right. So we'll set. So if count is less than 0, then what we want to do is read as much stuff as possible. So set that to the length of the queue. Okay. Oops. Okay. Iterate over that. So 4K in range count. And let's see here. Then data.append self.queue.pop left. Okay. Go, and then I will return. I'll return the data bytes. Okay, there we go. Don't need anything else. All right. So there we go. So that's what the test bench interface looks like here. You can read, which should block until data is available. And then you can also do read no wait, which will attempt to read whatever is currently in the buffer. And then on the source side, you can do the same kind of thing. You can call write to put stuff in the buffer. And the idea is that we can make this block if you want to specify, a maximum buffer size. We can implement that later. Okay, so now we need the actual implementation of each one of these things. All right, so this is how you write coroutines in cocotb. So we'll do async def, async def run. Okay, so then what we're going to do here is we need a while loop here, while true. Okay, so this piece is going to be written kind of like a standard Verilog test bench module, where you're going to have if you're making like a piece of non-synthesizable code, you'll have a loop in here that does something and then waits and then does something, Okay, so in this case, well, the first thing we need to do is pull something out of the queue. So while the length of the queue is 0, while the queue is empty, what we're going to do is sync.clear. We reset that, and then we're going to await it. Wait. Okay. And then when we actually have something, then we're going to go ahead and grab the byte. Okay. and then we're going to take that byte and we're going to shift it out. So how does a UART work? Okay, well, a UART, first thing you do is you send a start bit, right? So the start bit is low, actually. Now I need to add some more stuff, right? So we want the line to start high. So I'll set immediate value to set the data to high when you load the module. And then we will send the start bit. So I'm going to go ahead and mark this, the start bit. I will set the data to 0, and then I'm going to await some time value. All right, so how long are we going to await? We're going to await whatever bit period is, right? So we're going to use a timer for that. This is going to be, I'll specify this in nanoseconds because why not? Okay, so what we do is we take, 1 times 10 to the 9th nanoseconds per second. You divide by the baud rate. That gets you the number of nanoseconds per bit. Convert that to an int because timer gets annoyed when you give it floating point numbers sometimes. And then nanoseconds because that's the units that we're using. Okay, so we send a start bit. We wait for 1 bit, we wait for 1 bit time, and then we want to send the actual data bits, right? Okay, so 4K in range 8. I guess another extension that you can make to this is the ability to, let's see, the ability to change the number of bits per byte, for example. Right now, I'm not going to bother with that just for simplicity. So, writing that. All right, then, let's see here. So I'll do bit equals e and 1, right? So I'm going to write the bit value there, and then I do self.data is bit, shift that by 1. Okay, and then I await e. Okay, so we can see how this works, right? We set it to 0 for the start bit. We wait 1 bit time, and then we loop over all the data bits one at a time. We set that value, we shift by 1, and then wait t. So what we end up doing here is we send all the 8 bits one at a time over the link, and then we need to provide a stop bit. And we're sending them LSB first because that's kind of how UARTs work. Okay, so I think this is all we need for the source side. Pretty simple. Oh, actually, one very important thing that I almost forgot. We need to do cocotb.fork, oops, self.run. Okay, so this is what actually starts the coroutine, right? So let's go over how this works. You call write with some data, it puts it in the queue, and it sets sync. When you create this object, what it does is it, let's see, it calls set immediate value to set data to 1 because we want to start high. And then, see, what do we do after that? And then this run thing, this run coroutine has been forked. So when you write data into the queue, it will set sync. This thing will be waiting on that. Once it becomes set, then this will run. It will pop the byte out of the queue. Then it will drive it out 1 bit at a time, starting out with a 0 start bit, and then 8 data bits, and 1 stop bit. And at that point, then it will loop around again. If there is another byte, then it will go ahead and run. Otherwise, it will basically sit there and wait until something ends up in the queue. Okay, that's pretty straightforward. Now the sync, well, let's see. I don't need to set immediate value because I'm just reading. But what I will do, I'll go ahead and put the fork call here. Self.run, okay, here we go, and I'll define run here. So in this case, we're going to be trying to receive the bits over the wire. Okay, so async def run self. Okay, idea here, while true. Okay, let's see. So what are we doing? So what we need to do is wait for a start bit, and the start bit is going to be a falling edge. So we're going to do await falling edge self.data. Okay, there we go. Oh, and I actually need to define that up here, right? I don't need rising edge. Do I need rising edge? I don't know. I do need falling edge. All right, there we go. Okay, so I wait the falling edge. All right, and then what do we do? And then I need another timer. Right, I'm going to do exactly the same thing as before. Okay, and let's see. So we have a start bit. Now we need to wait half of the bit time. So I'm going to do this again here. Wait this, but divide that by 2. Okay, so if we wait half the bit time, then we end up right in the middle of the bit. So then we can receive the header bits. All right. And same thing here for k in range 8. Great. And then we're going to do await t. So we await 1 bit time. So when we start, we're at the beginning of the start bit. So we wait half a bit time, so we're in the middle of the start bit. And then we wait a whole bit time, so we're in the middle of the data bit. Okay. Whoops. Okay. Let's see. So now I'm going to do the same kind of thing here. I'm going to do bit equals self.data.value. Oops. Value.integer. Okay. And then I'm going to go ahead and print that so we know that we read something. Read bit k, there's the bit value. Okay, very good. B, oh, I need to create a, go. Okay, so we're going to build up our byte, and this is going to be bit shifted by k. And then what we do is we put in the queue. Put that in the queue, and then we do self.sync.set. Okay, and I think that's everything we need. All right, so these are the simulation modules. I think I have everything I need here. The next thing is in the init.py file, I want to export these so you can import them a little bit more nicely. So what I'm going to do here is I'm going to import, from UART, port source, UART sync. All right, that looks good. Okay, what else do I need? Okay, so in order to test this, I actually need to install this as a Python package. So in order to do that, I need one other little file here. Actually, I might need 2. Setup.cfg and setup.py. Okay, so this is all kind of boilerplate code that you need. There's not that much. Setup.py. This is for backwards compatibility. Pretty straightforward. Setup.cfg. In this case, we just need the kind of bare minimum for the package. Not sure what the minimum we need here is going to be. UART, so you need the name, and then we need a little bit of code. Anything else here? I think that's the main thing. What we need to do is tell Python how to find the package. So let's see here. Oh, options. Yeah, okay, this is fine here. Packages equals find namespace, because it's a namespace package. Okay. And options packages dot find is going to be include vx. I think that's all we need. Let me see if this is going to work. So what I need to do is install this as an editable package. So you do pip install-e dot. Okay, there we go. So it looks like that installed that. All right. Let me see if I can import it. Let's see, import cocotb x dot UART dot source. Can I do that? Oh, sorry, I want to import that. I can do, well, actually, from UART source. that work? Yes, that does work. Okay, cool. So now the next step would then be to write a very basic test bench for this. So I'll go ahead and do that. This should only take a couple of minutes to do that. All right. So one thing that's slightly annoying about cocotb is that I don't think there's a way of running tests in cocotb without simulator. So even though we don't actually have any Verilog code here, I actually need to create a very simple Verilog module with the single data signal in it that we can connect to. Okay, so let's see, module test UART. Okay, and then I need a single signal here. Now wire data, and that's it, right? Yeah, I think so. And the end module. All right, cool. So there's that, and now I need a Python script. All right. I need a Python script, and then I also need makefile. So I'll copy the makefile from another project here. Let me see. Do I have my cocotb extensions open? Yes, I do. Be the simplest, probably one of these. All right. Next, AXI. I'll copy that makefile. A bunch of stuff. The Ethernet ones that are going to be simpler. Here, and I'll copy. How about that? All right. There's no parameters in here, so that'll be perfect. Okay. Oh. There we go. Okay, so there's our makefile. Call this now test UART. Okay, good. And then I need to go ahead and fill in the very simple test bench for that. So same idea. I'm going to go ahead and actually copy that from the MII test bench here. And then we can strip out everything that we don't need. So this test, we test UART. Okay, I can get rid of all of this stuff. Rid of all of that. Okay, so that also, I keep doing that. Okay, so I can get rid of that. Okay, and in this case, now I want to import the module that is created, right? So from cocotb ext.uart import UART source, UART sync. Okay, that. Then I can go ahead and update this. So I got a clock. Actually, a bunch of stuff I can get rid of here, right? There's no clocks, and there's any triggers either. Okay, so I don't need the clock, don't need the source, don't need the sync. Well, I need to create new sources. Okay, self.source is going to be UART source, and let's see, connect this to data speed equals 9600, or again for the sync. There we go. I don't need reset. I don't need any of this stuff. All right. Very simple here. That goes away. All of that goes away. All right. I'm just going to delete all of this here. We'll start from scratch, basically. Okay. So what do we need to do? We need to very simply send some data over the UART and make sure we get the same data on the other side. So the first step to do here is to call tb.source.write, and I'll put some test data in here. Okay, now I'm going to do a timer. Oh, I need to import that, don't I? From cocotb dot triggers import timer. All right, let's see if this actually does something useful. I'll run make, and oh, because that wasn't speed, that was baud. And does it run? It ran. Okay. Source.write was never awaited. All right, I need to await that. Run this again. Bring an int. Okay, I think I forgot to convert something to correct type. Let's see. So where is UART.py? Be on the reading side. It's on the reading side anyway. Oh, I see. Okay, I know what I messed up. This needs to be a byte string. Okay. Okay, there we go. So now we can actually see, it looks like it read and wrote some bits. All right, let me see what this looks like in the test bench or in the waveform view. There we go. Okay. Make waves. Okay. Now if I open that up, GTK wave, test UART, UART.fst, and we can see that at one single signal, zoom out, and that looks like that could be a UART signal. All right, so now let's see if we can actually read all of the data. It looks like I didn't wait long enough. Let me wait like 10 milliseconds and try that again. All right, let's see here. That looks like UART data. Okay, so we're just about done here. The next thing I need to do is actually read everything out of the UART and make sure we get the correct result. Okay, so problem with the read command is that it only waits for at least one data byte. It doesn't wait until you have everything. So I have to actually do this in a loop while len. Actually, I'm going to do one other thing here. Instead of passing this directly, I'm going to add another variable, test data. So I will set test data to that, and then I'm going to do while rx data is less than the len of test data. I will loop. I do rx data dot extend. Let's see. Oh, and then await db dot sync dot wait. Okay, and then once this is done, then I will print rx data. Okay, let's see if that works. Oh, well, that was silly. All right, that should be receive, not wait. Not thinking straight here. Oh, read. Okay, third time's the charm, right? Hey, there we go. There's our test data, AA, BB, CC, DD, and that matches this. So right here, I can timer 1, and I can add cert rx data equals test data. Okay, there we go. It ran, test passed, and there we go. So that's what the UART sent. Looks good. We were able to send it and receive it. So that's how you make a very simple cocotb extension. So now we can take this and use it inside of a larger test bench for testing a Verilog design. All right. So I think that about finishes off everything that I wanted to do today. Are there any questions? Anything that anybody wants to see? Not, then I'll probably terminate the stream then. Thanks to everybody who dropped by to listen in.